Okay, let's get started. Today we'll be talking about probabilistic models. You've already seen some aspects of probabilistic models throughout the previous few lectures, but today we'll really dive into probabilistic models in a way that we haven't yet before. And so just to sort of recap where we are in this class, most of this class has been about supervised learning, and we're sort of beyond supervised learning at this point. And we spend a bit of time talking about unsupervised learning. And for the remainder of this class, I actually won't be drawing a distinction between supervised and unsupervised learning. There will simply be some sort of learning signal that we're trying to optimize, and there will be some assumptions, and then we'll design an algorithm or look at algorithms that can optimize this learning signal subject to these assumptions. And sometimes the learning signal will be completely supervised, like we've seen in the first 5 weeks of class. Sometimes they'll be completely unsupervised, like in eigenfaces. And then sometimes it'll sort of look a little bit in between, like these sort of partial supervision or weak supervision, like Amazon, purchase together type of signals, which aren't really kind of supervised labels that we've come to expect, at least for things like the Kaggle competition, but nonetheless, is not purely unsupervised either. And so I really won't be drawing the distinction anymore. It would just be there's some loss function, and we're going to optimize it. And the loss function will be constructed based off some assumptions we make about the data that we're learning on. And so today, we'll be looking at probabilistic modeling, which is the bottom right blue box, which tries to put everything that we've been doing on a sound probabilistic interpretation. We've already talked about maximum likelihood, and that's sort of just the tip of the iceberg. And everything I'll be talking about today will fall into the maximum likelihood framework. So the learning objective, after you define the probabilistic model, will just be maximum likelihood, which you can write equivalently as minimizing log loss under some model design. And today we'll start the first of 3 lectures that tries to sort of reason about careful model design of probabilistic models. Okay, so today, basic probabilistic models. And for the most part, we'll focus on a model called naive Bayes and what you can do with naive Bayes. And we'll, at the end of the lecture today, just give a brief overview of more advanced models. Next week, we're going to talk about hidden Markov models. And then keep in mind there's a recitation this Thursday, even though there's no lecture, on probability if you feel like you want to brush up on your probability of your recitation this Thursday. Okay, so probabilistic model, often also referred to as a generative model in machine learning, and is defined as the following. We have a distribution of, for the x and y. For the sake of this lecture, we'll keep it in the supervised learning setting where there's a supervised label, although we're going to see later on that the distinction between x and y start to become blurred after a while. But let's say the target variable we ultimately want to predict is the y variable. Then, if we model the joint distribution P of x comma y, we can make a prediction of the probability of y being, let's say, the positive label given observations x using Bayes rule. How many of you have seen Bayes rule before? Okay, so about 80% of the class. If something like Bayes rule is a bit new to you, no worries. It's a fairly standard tool in manipulations of probability, and you'll become quite familiar with it through the homework and through the recitation. So the Bayes rule is just basically the formula given above. P of xy is the thing we're trying to learn or fit to data. P of x can be computed via marginalization. So a marginal distribution, let's say just P of y or P of x, is just summing over the variables that we're not computing in this probability. So in the case of P of y, we're summing over all the other x's. So the sum over all possible x of P of y comma x will give you P of y. Similarly, the sum of all possible y of P of y comma x will give you P of x. And so given that we can compute P of x comma y, or excuse me, given that we can learn P of x comma y, then we can compute P of y given x using Bayes rule and marginalization. That's the basic idea. So here's an example. And again, since everything's a probability, we'll assume that p of x comma y sums to 1 if you enumerate over all possible xy pairs. P of x comma y is also known as the joint distribution. That's the thing we're trying to learn in this example. So, suppose that this is the model that we learned. It's a very simple model, so x can take on one of 3 values, just for simplicity, and then y can take on one of 2 values. So if I wanted to store this whole thing as an exhaustive enumeration of all possibility, then the p of x comma y model is basically a lookup table of size 6 in this simple example. And so we can ask questions like, what is the probability under this distribution that the x I observed is homework? And we can compute that via marginalization, the formula on the bottom. In essence, what we're doing is called marginalizing out the y. We can ask questions like, what is the probability that y equals spam given that x equals help? And the answer is 0.6. So the probability of x comma y, so for these two xy values, is 0.15. The probability of x, of this value of x marginalizing out the y, is 0.25, and then we apply Bayes' rule. Or sorry, this is just a law of diminishing probabilities. Example number 3. We can ask questions like, what is the probability that p of x equals help given that p of y equals not, or not spam? So this is kind of interesting, right? This is like normally the reverse kind of prediction task that you would normally see in a supervised learning task. In a supervised learning task, you learn to predict y given x, and what is y is specified up front, and if you're doing logistic regression, you're just minimizing log loss of p of y given x, and that's the thing that you can predict. If you learn this full probabilistic model, then you can, in which case, what I mean by that is you learn this joint distribution right here, then you can manipulate it however you want. So you can compute p of x given y. So we can see that these probabilistic models, assuming that we can learn them well, which is a big if, but these probabilistic models can offer a lot more flexibility in terms of the things you may want to estimate or predict about your data. It's not just restricted to what is the probability of a pre-specified variable y given x, which is what essentially supervised learning is doing in this paradigm or interpretation. Any questions? Okay, let's talk about training. So during training, the goal is to learn this joint distribution, p of x comma y. In this very simple case, it is a lookup table with 6 numbers in it, because we can just enumerate the entire universe of elements that we care to model. So what's the objective function? It's maximum likelihood, as I mentioned before. So given a training set, so again, the training set is a set of data points of all the attributes that we're measuring or observing, and assuming that they're sampled independently from the test, from some unknown test distribution, we maximize the likelihood. And because they're sampled independently, by maximizing the probability of the data set is equivalent to maximizing the product of the probabilities of the individual data points. And this, by taking the negative log of this maximization problem, is equal to minimizing the log loss of this particular model. It turns out, and I think we were going to go over a derivation if I recall later in lecture, that the optimal solution of this minimization problem is just frequency counts. So what does that mean? That means we look at our training set, and for any xy pair, we compute its frequency, its empirical frequency in the data. So for example, for y equals not and x equals help, that particular xy pair occurs 10% of the time in the training data. So those 6 parameters are estimated using frequency counts, and that is the analytical solution to the minimization to this minimization problem. Okay, So what is maximum likelihood saying here? It's saying the following. We have a specific probabilistic model. Here we're learning P of x comma y, the full joint distribution. And in this case, the model is not structured. It's just a giant exhaustive lookup table that enumerates overall possibilities. But that a lack of structure is also a structure in some sense. So given a specific probabilistic modeling structure, maximum likelihood says we're going to fit the parameters of that model that best explains the data. And so from a 10,000-foot view, this looks a lot like logistic regression. It's just that the specific model now is different than logistic regression, but nonetheless, we're just maximizing likelihood. And the game we play is to find different choices of model structures. Okay, so here's the training derivation. We're going to do a reparameterization. So we're going to reparameterize this probability as a ratio. So keep in mind that these probabilities are not negative and sum to 1, and if these W's are also non-negative, then this is just an equivalent reparameterization, nothing more. So just change of variables. So then we can write out this minimization of this log loss using this change of variables as follows. So I haven't done anything special here. But I'm just going to take it's a minimization problem, so I'm going to take the gradient with respect to these new change of variables, and if you just compute the gradient, standard multivariable calculus, changeable type stuff, you get that this is the gradient for any specific xy pair, the parameter associated with any specific xy pair. You set the gradient to 0. And you get that the optimal solution is a frequency count. So it's a very trivial 3-step derivation to show that the optimal solution is a frequency count. You don't even need to do this change of variables. The change of variables just makes this derivation a lot shorter. You can do it in the original derivation using the original variable as well. It's just a lot messier. Yes?
So just to be clear, so far you're not assuming that P of x, y is like some parameterized family of distributions.
It is a parameterized. It's an unstructured. Okay, let me see if I can interpret your question. So usually people assume, and I'll get to this in like a few slides, but usually people assume that there's some more structure in the model because obviously, and we'll talk about this later, in this particular type of model, as the number of possibilities increases, the number of parameters increases exponentially. And yes, I'm just assuming that. Nothing changes at a high level when I assume more structure, just more tractability. And that's the game that we play in these probabilistic modeling approaches, is how to keep things both expressive and tractable. Yes?
What exactly is W?
It's a change of variables. So recall that we have this lookup table. So these are P of xy is just is parameterized with these 6 variables. I'm gonna just do a change of variables and say P of xy is equal to W sub xy divided by the sum over all possible xy's. So now my 6 variables are W sub xy. Before my variables sum to 1, and now my variables don't no longer sum to 1, but they're mathematically equivalent by this relationship. So it's just a change of variables.
But it's not it's not the probability.
It is the probability if you divide by the sum.
Yeah, but I'm saying like what value in like the table on the last slide, what value would I plug in for W?
Well, let's say the sum of W is 100, right? Let's say the sum over all the W's is 100. Okay, so let's say the bottom is sums to 100. Then WXY would correspond to 15 here, 10 here, 5, 45, 20, and 5. And if you actually look at, and we don't actually use this W in practice necessarily. It's just a way to derive the optimal solution. One choice of W is W equals the number of x comma y, the number of times this xy pair occurs in the data, and then the sum over all W is simply the sum over all the data, the number of data points. Okay, as you can imagine, what I just described is prone to overfitting, especially for somewhat small data sets. And so you might consider, well, how do we regularize? The way that one typically regularizes in these type of models, well, one of the more popular ways, arguably the most popular way, although I haven't done a survey recently, so I don't know if it's still the most popular, but certainly historically the most popular way, is to hallucinate data. This technique is also known as pseudo-counts. So basically, and there's a few different ways to write this, so I wouldn't get too hung up on this specific formulation. But the basic idea is that we're going to hallucinate some data points according to some probability of observing x comma y. And then we're going to create lambda of such hallucinated data points. And lambda you can think of as a regularization string. What this basically saying is that in the absence of observing any data from the test distribution, I'm going to pretend that I observe some fictitious data from this particular prior distribution that I specified. Oftentimes it's uniform distribution. If you recall, in lecture 3, we talked briefly about hallucinating data as it relates to regularization. And so I invite you to go back to that lecture and read up on that just to see the connection. The connection is a bit more subtle in these probabilistic models. So the full mathematical connection to a more formal notion of regularization, I won't be able to go into completely, but for squared loss and L2 regularization, lecture 3 has a very nice connection. Okay, so let's talk about generative versus discriminative models. Everything I've described, up until now, looks a lot like logistic regression, just with some changes. And let's be concrete about what the differences are. Logistic regression model is also historically known as a discriminative model, whereas what I just described is typically referred to as a generative model. Now this distinction, I should mention again, becomes more blurry when you have a lot of these side variables where it's not clear that one of the variables corresponds to something you want to predict a la supervised learning. But in the case where one of the variables is that dependent variable that you predict via supervised learning, then this distinction is very sharp. So for example, a generative model models both y and x. So it models the joint distribution, q of x comma y. A discriminative model that's trying to discriminate on a specific variable y, so just like in supervised learning, trying to discriminate on a specific variable, is trying to model y given x. So the only thing it learns is probability of y given x. So this is logistic regression. So what are some benefits and drawbacks of these two paradigms? Well, for a generative model, you can tolerate missing data. So this is probably something that people thought a lot about in the context of the Kaggle competition and other things related to the Kaggle competition. If there's some x, value of x, if x is a vector of values rather than a single value, if there's some value of x that was missing, you wouldn't even know what to do with logistic regression. Like you could try some heuristics and hacks and just sort of paper it over, but like from a foundational point of view, it's not clear what you should do. With a full probability distribution, it's very easy what you can do. You can fill in that missing value because you have the full joint distribution. With logistic regression, you're stuck. You can try some heuristic or hack to cover it up, but otherwise, there's not much you can do. So that's what I mean by modeling the full joint distribution. In logistic regression, the only thing you're modeling is P of y given x. And if you are not given x, you can't do anything. Of course, what are some benefits of discriminative models like logistic regression? Well, logistic regression, if the only thing you care about in this world is predicting y given x, and you assume you're always given x when it's time to make a prediction, then a discriminative model like logistic regression will typically do a much better job at that. In other words, if the only thing I care about is predicting y given x, then that is what I'm going to learn. And that's the only thing I'm going to learn. So I'm going to define a model like this, such as via logistic regression. I'm going to minimize its log loss. Generative models are trying to model something completely different. And then, like the joint distribution, which is very, very different. And then after you fit a maximum likelihood to this guy, and you want to make this prediction, you have to do this ratio. And if you misestimate this guy even a little bit, dividing by something you misestimate can lead to very high variance mispredictions. In other words, the training objective is not designed to maximize the accuracy of predicting y given x. Okay, so what are some other benefits of generative models? So this is, I should mention, this is the main benefit of a discriminative model. So historically, the supervised learning was so popular because it's so useful in industry. You have some target label, you want to predict it as accurately as possible. So you have a very narrowly defined prediction task. You want to predict it as accurately as possible. So historically, this has been the dominant use case of machine learning in practice. And so people have relied on these discriminative models, like logistic regression, maybe with a deep neural net behind it, rather than a linear logistic regression. That's what the ImageNet competition was. And so this really was a driving force behind machine learning and machine learning research, and now machine learning deployment for many, many, many years. But it is only one of many possible tasks that we can do with machine learning. It's the most economically fruitful one, but it is only one of many. And so other things we can do, and in some sense, we can have a generative model do all the above. It just does all the above not as well as if you had a targeted model. So for example, because it specifies the full probability distribution or full joint distribution of P of x, comma y, we can draw samples. So we can say, this model actually should be able to reproduce my training set, at least, something that looks statistically distinguishable to my training set if I model it well, because I can just draw samples from my joint model. Right? I'm learning a model of the distribution, which means I can create my own hallucinated training set via drawing samples. And so I just wrote here a very simple procedure for sampling from this particular model, which is just a enumerated lookup table. And so it's basically what you expect. This is a very simple script, flips a random coin, checks if the coin is between some threshold. Oh, sorry, not flips a random coin. Draws a uniform random number, check if that random number is between various thresholds, and if it is, we output one of the following entries. That's it. I should mention, and I'll briefly touch on this at the very end of lecture, that if instead of x comma y, my training set was a set of faces, and I want to sample a new face from my distribution of faces, it's basically this perspective with a very complicated, gigantic, deep generative. Generative model can tolerate missing values. We can model the probability of, well, okay, not all generative models can, but a fully joint generative model can tolerate missing values, and you can model the probability of missing a feature value, and discrete models cannot do this. This next point is a contentious point. Some people think that generative models are more elegant because the generative model is a description of the of some process by which the data is generated, and some people who work on mathematical modeling find that to be telling a more complete story about the data. And this is particularly useful if we cannot decide what prediction task is going to be the one we care about a priori. We want to model the data first, and then decide on the prediction task later. Generative models allow you to do that. For discriminative models, every time you do that, you have to retrain the model because it's only designed for specific prediction tasks. Any questions? Okay, so for the bulk of this lecture, I'm going to talk about naive Bayes. So we're going to start with a setting that looks a lot like supervised learning. I'm going to have a variable y. I'll call it a binary variable y that I'm going to single out as having special meaning, and then I'll have a bunch of other variables I'll call a vector of x. In the simplest case, all the other variables x are also binary. For example, the presence or absence of a word. And I'm going to model the joint distribution P of x comma y. So an example might look like this, where if I have two x's and one y, then if I do a full exhaustive enumeration, I get 8 possible values in this lookup table. So as was already brought up before, the biggest challenge with this approach, even though it is a valid joint distribution over x-y pairs, the biggest challenge of this approach is that as the number of x's grows in dimension, the size of this lookup table grows exponentially. In other words, the complexity of this model class, which is unstructured, because it assumes no structure, it's just doing an exhaustive enumeration over everything. The model complexity is exponential with the length of x, which is not desirable. And so naive Bayes is one way to get around this. And this is a very, I would say even to this day, people still use the naive Bayes model for many prototyping and hypothesis testing tasks. So naive Bayes posits the following generative model. And for those of you, how many of you, I'm curious, have seen a graphical model diagram before? Okay, so not too many. So the graphical model diagram is the thing you see on the right. What it does is it posits a generating process. So what that means is that the graphical model diagram gives you the structure of the probabilistic generative model. In this particular case, it posits the following generative process. First, we sample y, so we have a probability distribution over y. And then, given y, we compute the probability of every x given y independently. That's what these arrows mean. These arrows mean that this arrow from y to x2 or x1 means that if we condition on y, so if we observe a certain y, the probability of x2 given y is completely independent or conditionally independent of all other variables. That's what this graphical model diagram is saying. In this previously unstructured setting, the graphical model would be pointing in every direction. It would be like a complete graph. Here it's not. And so what that means is that we can write out the joint distribution as its product. And every term in this product corresponds to one of these arrows. So in other words, The only probabilities that we need to keep track of are these. Probability of y, and probability of xd given y, where d is one of the capital D variables in the x vector. The reason why this approach is called naive Bayes is that it makes what is now known as the naive independence assumption. So why is naive Bayes convenient? Well, it has a compact representation. Each of these tables is a 2 by 2 table. So it does not, number of parameters does not scale exponentially with the length of x. It scales linearly with the length of x. It's easy to estimate these components. So we're going to look at a maximum likelihood formulation where, again, this reduces to counting. It's easy to sample from. It's easy to deal with missing values. So let's just look at a very simple example. So here, the length of the x vector is 2 in this very simple example. And so here is the probability of p of y, which is a lookup table size 2. And then here are the probabilities of p of x given y. Excuse me. And this is the entire model. So what this says is that, if I look at the data set, the probability in my training set, the probability that an email is spam is 70%, probably underestimated for modern data sets. And the probability that an email is not spam is 30%. So that's just an empirical estimate of my training data. And then condition on my email being spam, the probability that we observe, the probability that x1 is 1, which corresponds to, let's say, the presence of word homework, let's say, is 20%. The probability of x2 being 1, which corresponds to the presence of the word winner, is 50%. And then if the probability of y is not spam, if y is not spam, the probability of x1 given y is 60%. So the probability of observing the word homework in the email, condition on the email not being spam, is 60%. And then the probability of x2 given y is not spam is 10%. So the probability of observing the word winner, given that the email is not spam, is only 10%. So that's how you can interpret these probability tables. And again, look, one thing that's interesting is that we're modeling p of x given y, whereas logistic regression models p of y given x. As I mentioned before, the model complexity is now linear with the length of x rather than exponential. Okay, so how do we make predictions? Suppose we want to predict p of y given x. Again, for these probabilistic models, we can predict whatever we want. But let's say we want to do the standard supervised learning prediction problem, which is predicting p of y given x. That's defined by this formula up ahead. And then we can factorize this part into using the laws of initial probability. This whole thing is called Bayes' rule. And then we can further factorize this p of x given y as the product of an individual xd's given y, because we made this conditional independence assumption. This is the naive Bayes assumption right here. So the first two equalities is just Bayes' rule. The next equality is specific to naive Bayes. And now we observe that this is just proportional to this quantity. So we can ignore p of x in the denominator because it's fixed for x. For any condition on x, this bottom part is fixed. So we don't need to actually compute what it is. We just need to compute everything in the numerator, and then divide by the sum over everything in the numerator because it's just proportional. And in fact, if we look at this, this is actually everything we keep track of. This is something that is explicitly in our model. This is just a lookup table. Everything in here is, again, just a lookup table. So now, through this fairly simplistic manipulation of p of y given x, and making one assumption about the structure of naive Bayes, we've reduced computing P of y given x as just reading off values in our parameter tables. It's a very, very simple computational task. Right, so we can go over a numerical example. Suppose that P of y equals 1 is 30%, and P of y is the negative class is 70%, and then P of x given y is positive class is 5%, P of x given y is the negative class is 0.1%. Then P of y given equals 1 given x is equal to 96%. So even though observing this particular x value, so x could be an entire vector, even though observing this particular x value is quite rare, the fact that we observed it, condition on the fact that we observed it, then we can be fairly likely that y is the positive class. Okay, example number 2. Here's a sort of a non-standard prediction task. Suppose I want to predict x1, given having observed all the other variables. I observed x2 to d, I observe y, and I want to predict the probability of x1 conditioned on the other variables. Okay, naive Bayes allows us to do this. It's very simple here. Because of the conditional dependence assumptions, probability of x1 given y is independent of all other variables, so it's just a lookup table. Or it's part of a lookup table. Simple. Okay, suppose we want to predict probability of P of x1 given observing P of x of 2 to d. So notice here that we don't observe y. So y is not observed. We didn't measure it for whatever reason in this particular prediction task. We only measured x2 to d and want to predict x1. Again, we can just say, okay, well, we're going to manipulate we're going to just do some probability manipulations. And again, we're going to, if this type of manipulation is new to you, the recitation on Thursday will go over this, a few more times to help you get more comfortable. But there's nothing too crazy happening here, right? So this is just the fraction, the ratio of P of x given P of x2 to d, because this is the joint distribution over P of x1 to d. And then this is equal to marginalizing out the y variables. And these are everything in here is now things that we can look up, we can compute by inspecting our lookup tables, probability lookup tables. Now, one thing you might ask, just from looking at this formula, is like, wow, there's a lot of things going on here. Is this thing actually a probability? How can I be sure that the numerator is smaller than the denominator? And the thing to keep in mind is that for these types of, and this is a sanity check you often want to make. So if you're writing out a probabilistic model, you're trying to write out some formulas for inference, and you're debugging your code, you want to do some, or even debugging your mathematical derivation, and you want to make sure things are correct. And this is like an example of a sanity check you might want to make during the development and derivation of your approach. And if you ever do this, and again, and you will do this for homework 6, I encourage you to do these sanity checks often. It'll make debugging a lot easier than not doing it at all until the very end. So here's a sanity check. What makes me think that the numerator is smaller than the denominator? If it's a valid probability, this should always be the case. That the numerator is no greater than the denominator. And the thing you can observe is that, well, this P of x given y is a product, right? By the naive Bayes assumption, it's this product. And P of x2 to d given y is also this product, but missing P of x1 given y. So the numerator has a product whose set of terms is a superset of the set of terms in the product in the denominator. In the denominator. And since every term is upper bounded by 1, multiplying by more things that are less than or equal to 1 can only decrease your value. Therefore, the numerator must be no greater than the denominator. In fact, the only time that the numerator is equal to the denominator is if p of x1 given y equals 1. Whenever p of x1 given y is less than 1, then the numerator will be strictly less than the denominator. So sometimes people write things out in matrix form, simply because sometimes it can be cleaner to write these things out in matrices, and given all the parallel computing that is possible these days, writing things out in matrix form may offer opportunities for parallelization and speed up compared to just having a serialized computation. And so this is not universal, but people often refer to the prior matrix as P, and this matrix P of x given y is the observation matrix, or O. And then you could write out things as dot products. This isn't so relevant to this class. I'm not going to I'm not going to fixate on this type of matrix form too much in this class. It doesn't matter so much, but it's important to understand that this concept exists because parallelization and computational speed up are very important in machine learning these days. Okay, missing values. So what if what if we don't observe x2? So let's say d equals 2, and we just want to predict p of y given x1. So again, we could write p of y given x1 as as marginalizing out p of x2 to d. In this simple example, d equals 2, so just x2, and then we could write this out as the following. One thing that you might ask is that this one looks a little complicated, right? So naively, this summation seems like it's summing over an exponential number of possibilities if d is large. So how can we efficiently sum over multiple missing values? So again, in naive Bayes, we can exploit the structural definition of naive Bayes. So this is the structural definition. This is the structural assumption of naive Bayes right here, the formula. And it turns out, because of condition dependence, I won't go into the details, that there are some manipulations you can do to make that sum very efficient. And so these are the reasons why people build in these conditional dependence assumptions, is that if you have the right set of conditional dependence assumptions, suddenly a lot of complicated prediction tasks that look like they're naively going to have to sum over an exponential number of possibilities, by exploiting the structure of your model, you can collapse it down to something that's much more tractable. Both in terms of the number of parameters, so it's more statistically efficient, you can fit the parameters with less data, and also computationally more efficient because the inference procedure or the prediction procedure through exploiting the structure of your model avoids these exponential time blowups. Of course, it's not always the case for really complex models. You can't avoid exponential time blowups, but even then, the structure may help you do these predictions a lot more efficiently than a naive, exhaustive enumeration. I think, in the interest of time, I'm going to skip this slide. You can look it over yourself offline, but I found that it's not particularly useful to go over this slide in class. Okay. So just to summarize the comparison with logistic regression, naive Bayes, we've seen that it can query any conditional distribution, P of y given x, P of y given x1, P of x1 given x2. Training the model via maximum likelihood of the joint model is just counting. The next slide is a mistake. The problem, of course, is that the training objective is not maximized for classification accuracy. So if you only care about P of y given x, then maximum likelihood of P of x comma y may not be what you want to do. So in contrast, logistic regression, known as a discriminative approach, the only thing it can do is predict P of y given x, and you have to observe all of x to predict P of y. Training is a little bit more complicated. You have to train using gradient descent. It's not a big deal these days, but it's a little bit slower. And you're trained to directly minimize log laws of P of y given x. So if predicting y given x is the only thing you care about, and oftentimes it is the only thing that you care about, then you should probably train a logistic regression model. So, in terms of predicting y given x, if that is truly the only thing you care about, then naive Bayes is truly awful. So here's an empirical comparison that was done several years ago. So these numbers, neural nets are typically much higher now because training them, we can train much deeper neural nets. But if you just look at these numbers, naive Bayes is pretty bad. So truly, if you really truly care about predicting P of y given x, I would recommend not using naive Bayes. But since now we're in the post-Kaggle competition phase of the class, I'm going to be talking about things that aren't so hyper-focused on predicting P of y given x. If that's all you care about, perhaps you could just stop taking the class right now and move on to other things. But we're going to talk about things that don't just rely on that. Okay, so training of naive Bayes is, again, via maximum likelihood. So we specify the structure of a model. This is a naive Bayes structural assumption. And then here, in this particular, if we make no other assumptions except for this assumption, then everything in here is a lookup table. We can make more assumptions. We can do hierarchical naive Bayes and make more and more assumptions. I'll talk a little bit about that at the end of the lecture. But if we make no other assumptions, then basically this is the structural assumption of the model, and everything inside is a lookup table. That's the basic idea. And so given this particular structural assumption, we're going to maximize the probability of the training set, which is equivalent to minimizing the log loss, as you see here. So everything at this super high level view looks exactly the same. It's just subject to the naive Bayes structural assumption. And again, it's just counting. So the probability of y equals spam is just the number of times that in our training data, y equals spam divided by the size of the training data. The probability that x1 equals 1 given y equals spam is just the number of times that in our training data we observe y equals spam and x1 equals 1 divided by the number of times y equals spam in our training data. We can add pseudo counts. So here you have to be a little careful because these two lambdas are not directly comparable because they may sum or divide over different sizes. But roughly speaking, you can add pseudo counts to each individual probability lookup table. So this is actually what people do for regularization. Yes?
Is this equivalent to bootstrapping, or is there something different that you're doing? Like,
Oh, so under some specific modeling choices, you can show that you have a prior. Yeah, so imagine that these are Bernoulli random variables. Yeah, so these are basically Bernoulli random variables. So y is a Bernoulli random variable. P of x given y is a conditional Bernoulli distribution, right? And I don't know how much you know about conjugacy, priors and stuff like that. Okay, so the beta distribution is a conjugate prior to the Bernoulli distribution. And so actually you can show that in the case of this very simple case, that this is basically imposing a beta prior, a uniform beta prior. Or sorry, according to if this is uniform, then it's a uniform beta prior.
yeah, but in the case where we're not like imposing like the structure on the model by having like parameters like in a Bernoulli distribution or a beta distribution, or just using the counts, then when I'm generating new data for this,
Then it's literally just I, the designer of the model, believe that in the absence of training data, this is the fictitious data I should fit my model to.
Okay.
That's it.
Okay.
I would not go any further than that. Yeah.
Okay.
You're not bootstrapping. You're not sampling from the existing data set.
Mm-hmm.
This process works in the absence of training data.
Okay.
That's what regularization is.
Okay.
So there are complicated distributions where conjugacy fails.
Mm-hmm.
And in which case, you can still fall back to this intuition of, in the absence of training data, I, the designer of the model, believe that you should fit your data to this fictitious data.
Okay.
But in this particular case, if you're familiar with conjugacy, this is basically saying that I have a beta prior.
Okay.
Okay. And yeah, for deep generative models, nothing's conjugate, so. Yeah. Okay, sampling. So we can sample from the naive Bayes distribution, naive Bayes model. So if we fit the model to data, we basically said that we believe that the training data can be sampled. We can sample something that looks qualitatively or statistically indistinguishable to the training data by sampling from our training model. So the way you sample is that you read off of, you sort of look at this graphical model, and then because this particular graphical model is acyclic, and most of the graphical models we'll be talking about are acyclic, then you can just define a topological sort over the variables via this directed graphical model, and then just sample according to that topological order. So what that means in this particular case is that first we sample P of y, because P of y doesn't condition on anything else. We can sample it by drawing a uniform random variable, and then generating a value for y given some thresholds on this random variable that are determined by the probability lookup table. And then one valid topological order is after you look at y, you look at the x's in order x1 through xd. Since none of the x's depend on each other, any permutation of the ordering is valid. Let's just do x1 through xd. Then we'll again draw another uniform random variable r. And then we basically look at the probability lookup table of xd given y. And because we've already sampled y, we observe y. And then we assign a value to x. And we just go through this whole thing. And after we've done this for every variable, we've drawn a sample from the joint distribution. So here's just a simple example. We have two x's, and we have this lookup table for y. So the prior probability of y equals spam is 70%, the probability of y equals not spam is 30%. So we sample a uniform random variable between 0 and 1. This is a standard function built into every programming language these days. So it's available in Python. We get 0.5, so we're going to set y to spam. And then we sample another uniform random variable between 0 and 1. And then from that, we're going to sample x1 to be 1 or 0, given y equals spam, because we already sampled y equals spam. And we sample the random variable 0.1, so we set x1 to 1. And we do this again. And we could repeat this process to generate as many samples as we want from this distribution. Again, because there's no dependencies between x1 and x2, they both only depend on y, this process can be done in either order. Okay, so I guess I'm just going to do it again. So I'm going to sample uniform random variable, 0.9. So I set y equals not spam. And now I'm going to look at the lookup table that corresponds to y equals to not spam, and sample another random variable, and set x1 to 1, and do this again. Any questions? Okay. So just to recap, we looked at naive Bayes, which is, in some sense, the most fundamental generative model. It's certainly the simplest. It's a probabilistic generative model. It makes extremely strong independence assumptions. And because of those extremely strong independence assumptions, you get a very compact representation. So the number of parameters you need to store to fit this to capture this model is linear in the number of x variables. It's easy to train. Again, you can derive that the fitting these parameters is just frequency counts using the same trick I showed you in the beginning of the lecture, but with the change of variables. You can do it without the change of variables, but with the change of variables, it's much easier. Easy to compute various probabilities. And of course, it's typically not the most accurate for their standard supervised learning prediction task. In fact, it's often the least accurate. But it's, in terms of conceptual ideas, it captures all the concepts that are embodied in what people want to do with these joint generative models. The reason why we went over naive Bayes is that it has all the ingredients of this building of the things you want to do with generative models. And of course, in practice, you may want to do something more complicated. So you can invent your own model, right? Here's one I just made up on the spot. Suppose we had two variables that we want to give special meaning. I'll call it y1 and y2. So p of, again, I could write out p of x comma y, and then because this is the structural assumption, it's equal to y can be written, p of y can be written out as p of y1 given y2 times p of y2, and then the x's the final xd depends on both y1 and y2, but the other x's from 1 to d minus 1 only depend on y1. So this is the structural assumption of this particular generative model. And in the absence of any further structural assumptions, each of these terms is estimated using a lookup table. And then you can, I haven't actually verified this for this particular model, but I think this model is simple enough that all the standard inference tasks or prediction tasks you can, again, compute fairly efficiently by just manipulating the laws of probability. Sampling is, of course, easy. You first sample y2, then you sample y1, condition on y2, and then you sample x1 through xd in any order. Okay, so I'm going to go over a few, just a brief survey for the remaining 10 minutes or so. We can do Gaussian naive Bayes. So now, each x variable is continuous rather than discrete. So now a lookup table no longer suffices because each x variable is continuous. And instead, we can, instead of estimating a Boolean, like a Boolean probability, excuse me, we're going to make another assumption. And the assumption is that P of x given y follows a Gaussian distribution. And the parameters of a Gaussian distribution are its mean and its standard deviation, or its variance. And so now each of these little blocks has associated with it these two variables. So sorry, I should have mentioned. I'm assuming that y is binary and discrete, just like before, but x is continuous. Okay. So the independent structure looks exactly the same as naive Bayes. It's just that the output, each of these arrows is represented not by a discrete probability lookup table because the x is no longer discrete, but by the parameters of a Gaussian distribution. Yes?
Why doesn't the model also have
okay. The question is about the graphical model diagram. So it is certainly true that the graphical model does not capture all the information about the model. The purpose of the graphical model is to capture the conditional independence assumptions. So this graphical model can encode both real value and discrete value models. It makes no comment on that. The only thing it's commenting on are the structural assumptions in terms of the conditional. I see the question. So the only thing it's commenting on are the conditional independence assumptions. So everything can be written in terms of these guys. The form of these guys, it makes no comment on. Yes?
Are you assuming sigma is the same for all d?
You can estimate it. Oh. I guess in this particular case, I'm assuming sigma is the same. Of course, you can estimate it. Yeah. For individual pieces of the model. We're going to spend a long time on hidden Markov models next week. Hidden Markov models are sequential generative models. You have a sequence of, let's say, words. And we want to model the probability of that entire sequence. And in fact, we're going to spend so much time on it that it will also be the topic of this is not only the primary topic of homework 6, it is also the topic of mini project 3, which is the last assignment of the class, where you fit one of these sequential generative models, a hidden Markov model if you want, to a data set of Shakespearean sonnets, and you have to sample a new sonnet. And we'll have it won't really be a competition, but we'll have like a showcase where you submit your best poem onto Piazza, and the TAs give you an honorary prize, I guess, to the most interesting sonnet. Was that a question? No. Oh. I guess I won't spend too much time on this because it'll be the topic of the next 2 lectures. But I just want to point out that if you look at this, if you look at the graphical model, it says first you sample y1, and then condition on y1 you can sample x1, and then condition on y1 you can sample y2, and then condition on y2 you can sample x2, and so on and so forth. So you can just you could write out the structure of the probability using this product. And again, at this level of abstraction, we're not making any comment on the form of these guys. x. And so if they're discrete variables, then without any further assumptions, then each of these has to be a discrete probability lookup table. You're going to do Gaussian mixture models. This is basically the probabilistic version of k-means clustering that you may or may not remember from a few lectures ago. So the basic idea is that we have three cluster centers, if you will, and each cluster, or basically three clusters of. Well, so let's say Y has three. Let's say Y has three categories. So Y is trinary in this example. So Y is trinary, and then condition on one of the Y's, it's associated with a mean and a variance, and we generate X according to that condition on that Y variable. And then we have a prior probability of each of the three Y's. So we can sample one of the Y's one of three values. Condition on that Y, we sample with X according to its Gaussian distribution. And then and we assume that the training data that we observe is generated according to this process. So we fit the prior probability distribution of the three Y's plus the mean and the variance in a way that maximizes the likelihood of observing the data. So this is just a probabilistic version of k-means clustering. Yes?
Can you say what the membership variable means?
That's why. Sorry, I should. Yeah, sorry. As I often comment on, machine learning is this confluence of many different fields, and so the terminologies get. It's kind of like English, right? English is like this bastardization of multiple languages. So like some words, the way that things are spelled don't even make sense. I before you, except after C or whatever, right? So machine learning has suffers from a similar identity crisis. So membership is borrowed from the statistics community, which corresponds to just P of Y.
Okay.
Yeah. Are you a member of this Gaussian or this Gaussian or this Gaussian? Each individual X that you sample. Okay, you can go even crazier. So this is now a hierarchical. This is a hierarchical probabilistic model with multiple hierarchies of sampling. So I don't want to get too bogged down into the details, but this is what's called a plate diagram. What that means is you sample theta, which is the topic mixture of a document. So this is for modeling documents. And let's say there are capital M documents. This plate diagram means this block is replicated M times, because that's the training set. And then given that I sampled a topic mixture of documents, for every word in that document, let's say every document is exactly n words, although you can generalize from that. Every document is exactly n words. For every word in that document, it's an unordered, this is unordered, so it's a set of words. I sample a specific topic from topic mixture. And then given that topic, I sample a word. So there's two levels of nested hierarchies of this kind of sampling going on. And you could fit this model, the parameters of this model, to a data set of documents. And one of the things that are interesting about these types of models is that once you fit them to a document, you fit them to documents, you can actually start looking at topics. So you can actually look at, let's say I want to look at this arrow, right? I want to look at this arrow between topics and words. I want to see, okay, if I try to fit this model to a data set of documents to maximize likelihood. Now I can inspect what the model has learned. And in particular, I can look at that particular arrow, right? This is fit from, I forget what, oh yes, that's right. I Googled, so about a year and a half ago, 2 years ago, I did a Google search of latent Dirichlet allocation. This was the top result on Google search for LDA example. I don't know if it still is the top result, but it was as of 2 years ago. The reason I say this disclaimer is because this particular example is political in nature. It is an LDA analysis of Sarah Palin's emails, which were, I guess, you can, when she was governor of Alaska. And so you can identify these different topics. So this is the Z. So for the topic, wildlife, BP corrosion, these are the words that tend to have high probability condition on this topic, and so on and so forth. So this is an instance of an unsupervised probabilistic model, where we only observe X and there's all these other variables that form this like low-dimensional summary or reconstruction of the data. Okay, and you can do the following. You could actually look at an individual document and try to predict the most likely probability of a topic according to that according to the model. And probably the thing that is sort of most exciting these days are deep generative models. So, generative models that have, rather than having some probability lookup table somewhere in it, or sorry, rather than being fully specified by these probability lookup tables or very simple parametric models like Gaussians, somewhere in this probability distribution, the P of y given x or P of x1 given y or whatever is modeled using a neural net. This has also created a phenomenon known as deep fake. How many of you have heard of deep fake? Because about half the class, where these deep generative models fit to distributions of real data, like faces, let's say. And that face is not real, by the way. That person does not exist. Are so realistic that they're starting to create concerns of deepfake. We can do audio generation, so WaveNet is a deep generative model trained to synthesize audio given words. So it's sort of this weird thing in between supervised and unsupervised, where it is a conditional generative model conditioned on words, but otherwise there's a lot of complicated distributional things happening in between in terms of the audio waveforms. This is actually what's used in if you have an Android phone, WaveNet is what's used to synthesize the Android assistant. Again, this is a lot more complicated than what I talked about earlier today, but of course, what I talked about earlier today are the core principles from which these complicated models, evolve from. This is a project I worked on in sports analytics. You can generate hierarchical behavior over distributions of gameplay. This is fit to professional games recorded from the National Basketball Association. Yeah, I guess I'll skip the description of the rightmost figure. If you're interested, you can read the paper. Okay, so just to conclude, today we looked at a recap at a high level of deep generative models, generative probabilistic models, and then we did a deep dive into the simplest version, which is called a naive Bayes approach. And these generative models, because they model the full joint distribution, they look at they're allowed to look at many different slices of the data and give you probabilities of things that a normal discriminator model cannot compute. They are not trained to optimize prediction accuracy. They're trained to maximize the likelihood of the model generating the data, the training data. And you can use it to generate new samples, which combined with deep learning more recently has enabled many new applications for deep generative models. The next 2 lectures, again, there's no lecture on Thursday. The next 2 lectures next week will be on hidden Markov models, and there will be a recitation this Thursday on probability. And finally, I just want to make a plug. If you are free this Thursday, or you feel like you have space in your brain to learn about science, there's an emerging neuroscience symposium happening in this room all day on Thursday, and I'll be there all day. That's it. Thank you.